Hey guys, sorry I had to be out again today. Unfortunately, my daughter came down with a fever tonight and my wife can't stay home with her, so I will be home today. For Friday, I left you guys this problem, so I wanted to go over that with you. And then I've left a direct measurement video lab for you guys to do. I know you're thinking, yay, another direct measurement video lab. Alright, so for part A, guys, the question was derive an equation for how long it takes the stone to hit the ground after it's been thrown horizontally. So this is just a plain horizontal launch problem. So I'm going to start off with a kinematic equation for the motion in the y direction. And for this problem, v naught y is 0. Delta y I'm just going to sub in as h, and a I'm just going to sub in as g, so h equals 1/2 gt squared. And then I can just rearrange that for t. So for this problem we end up with t equals root 2h over g. So for part B they ask us to figure out what is the velocity of the disc with the person on it after they throw the stone. This is a little confusing to me because there is friction between the disc and the ice, but they do tell you the time of the throw is negligible, which means basically if it doesn't take any time, there is no time for friction to act. So we're going to treat this as a typical explosion problem where the linear momentum is conserved. I'm going to go ahead and do that on the next page. So for this problem, the initial momentum is going to equal the final momentum, and both of those are going to equal 0. So I'm going to go ahead and set up that equation. So here we see that 0 equals mv0 over 20, because that is going to be the momentum of the stone, plus m over 2, the mass of the disk plus the mass of the person, times their final common velocity, which I've noted as v. So then I'm going to do some algebra to rearrange for v. Alright, so at this point I will notice that the m's do cancel, and then I can finish up my algebra rearranging for v. So v comes out to negative v0 over not 60 but 30, and the negative don't want to erase. So the negative tells me that that is to the left. They did ask for speed, so it would be fine if the negative was not on your answer. Alright, and then part C says how long does it take the disk to come to rest? So now we are going to deal with friction. So when we're looking at this, if I consider the disk and the person together with a mass of 3m over 2, then I'm going to have my normal force going up, 3mg over 2 going down, and my force of kinetic friction, which will be my net force, going to the right. And you can solve this with either net force and then kinematic equations, or you can do the impulse momentum theorem. I'm going to set it up for the impulse momentum theorem. So here we get the force of friction times time as my impulse, which is going to equal my total mass of 3m over 2 times my change in velocity, which is 0 minus v. So now I'm going to sub in for Fk, and I'm also going to sub in for v. Alright, so we get mu times 3mgt over 2 equals 3m v0 over 60 once we sub everything in. And then now I'm just going to cancel out my m's and rearrange to solve for t. Alright, so now that I've canceled out the 3 on each side and the m on each side, rearrange for t, I get t equals v0 over 30 mu g. Alright, so now we'll go on to parts D and E. Alright, so for parts D and E, they've changed the problem a little bit. They have put a fixed axis in the middle of the disc, and now the person is going to throw the stone tangential to the circle, which should cause the disc to spin. For this problem, there is a net force on the disc through the axis of rotation that's fixed, but there is no net torque on the system, so the angular momentum should be conserved. So Li should equal Lf, which should equal 0. And then they've asked us to solve for omega for the disc, which does have the person on it. So I'm going to set up that equation. Okay, so here we see that 0 equals m over 20 times v naught r, because the stone is going to go up from its position we see in the figure there, which would give it a counterclockwise angular momentum, and then the disk and the person are going to have a clockwise angular momentum to make up for that, which will be mr squared over 2 plus m over 2 times r squared for the total moment of inertia of the disk and the person times their common angular velocity omega. And so now I just have to rearrange for omega. So at this point I have moved over the m over 20 times v naught r, combined my like terms for my moment of inertia, and canceled out my m and canceled out a single r on each side. And then finally, to solve for omega, all I need to do is divide by r. So we get that omega equals negative v naught divided by 20r, and the negative once again just tells me that it is in the clockwise direction to offset the counterclockwise angular momentum of the stone once it's thrown. For the last part, they say, what if the person is standing, instead of where they are, what if the person is standing halfway between where that red X is? And they want to know what's going to happen to the angular velocity now. Well, there's two things I'm going to notice are going to happen there. One is that the angular momentum of the stone is going to be half as much because it's at a distance of r over 2 from the axis of rotation now. The other thing I'm going to notice is that the moment of inertia of the disk and the person are going to get, well, the person's going to get smaller, the disk's going to stay the same, so the whole system, the moment of inertia, is going to get smaller. What you will see is that the final angular velocity does come out less than, and the angular momentum of the stone gets smaller, and that's a bigger effect than the decrease in the moment of inertia of the person. And just to prove that to you, I'm going to rework the equation we did from part D, but with the new moment of inertia of the person being at a location of r over 2. Okay, so here we have our new equation, and we'll notice a couple things have changed. The radius of the stone has gotten smaller, and then we'll also notice that the moment of inertia of the person with where they're standing in relation to the axis of rotation has changed as well. So now I'm going to go through and do the same algebra to solve for omega again. Alright, so as we can see, when we go through and do the same algebra and solve for omega again, we get that omega this time equals negative v naught over 25r compared to the negative v naught over 20r that we got the first time. And once again, that is because the angular momentum of the stone gets to be half the size due to the new value of r over 2 versus r. But we do also see that the moment of inertia of the person disk system decreases as well, but it's not enough to offset the angular momentum. So omega equals negative v naught over 25r, so it is less than it was for part D. Alright, I hope that makes sense, and you guys do have a direct measurement video lab to work on now, so go ahead and work on that through the end of class. If you don't finish in class, I think you know what to do. See you guys tomorrow.